Hi everybody, welcome back to AP Chemistry Chapter 7. Today we're going to talk about Sections 3 and Section 4. Section 3 first deals with the atomic spectrum of hydrogen. And there are two different types of spectrum. And both are created from excited electrons returning back down to the ground state. If you look at a continuous spectrum contains all the wavelengths of light. It contains all the visible wavelengths of light. You get this when light is passed through a prism. You're able to separate it into the wavelengths, and it's the whole Roy G. Biv spectrum of light. That is a continuous spectrum. However, you can take certain elements. You can make light bulbs, say, only filled with hydrogen gas, and excite hydrogen's electrons and allow them to return back down to the ground state. And there will be a color of light that's released from that light bulb. But if you pass that through a prism, you will not have the whole continuous visible spectrum. You will only have specific wavelengths of light, specific ones only to hydrogen. That is a line spectrum or discrete spectrum. And I want to show you real quick how that is made. Bye-bye, Jess. See you tomorrow. So here's the electron in hydrogen moving around its nucleus. It can absorb energy and move to a higher energy level away from the nucleus, but that's unstable. So eventually it will return back down to the nucleus, and when it returns back down to the nucleus, it releases energy as photons of light. And it only releases specific wavelengths. I'll show you some of those with different elements tomorrow in class. Okay? This is the idea here, that if you have white light, you pass it through a prism, you get all the wavelengths of light. That is your continuous spectrum. However, if you have, say, hydrogen gas inside of a light bulb instead of white light, pass that through a prism, notice you're only getting 4 distinct lines. You're getting 4 separate wavelengths of light. That is called the bright line spectra of hydrogen, and it's discrete. It's a line spectrum because it's not all the wavelengths. That's the difference between those. Okay? So again, how is the spectrum produced? The spectrum is produced when excited electrons return back down from the ground state and they release energy. It was first discovered with hydrogen, though we know that other elements can do it as well. And what it means, since there's only specific wavelengths of light, is that the energies of an electron moving, just like we talked about with other waves, the energies for electrons moving are quantized. Hydrogen's electrons can only absorb and release specific packages of energy. Okay? Section 7.4 deals with calculating the energy absorbed or released in a hydrogen atom. And there is, of course, an equation for that. And I'm going to show you this equation here. This equation for energy is equal to negative 2.178 times 10 to the negative 18th joules times z squared over n squared, where z is the atomic number of hydrogen. And I think you have this written down. I think on your notes it says nuclear charge. Nuclear charge is the atomic number. So for hydrogen, z will always equal 1. And n is the energy level associated with the electron. Okay? So we can actually calculate the energy associated with a particular energy level for hydrogen, where z is 1. And again, I have something here I want to show you. I think this will give you the line spectrum.
The discharge tube is filled with hydrogen gas. When a high voltage electrical discharge energizes the gaseous atoms, light is emitted only at specific wavelengths. The emission spectra obtained are called line spectra.
So there's another example of a line
In the
spectrum.
hydrogen emission spectrum, there are 4 lines in the visible region. A purple line at a wavelength of 411 nanometers, a dark blue line at a wavelength of 434 nanometers, a green line at a wavelength of 486 nanometers, and an orange-red line at a wavelength of 656 nanometers. Let's look at the electronic transitions responsible for the observed line spectra. When an electron drops from a higher energy orbit to a lower energy orbit, a quantum of energy, a photon, is given off in the form of light. During the electronic transition shown, light is emitted in the visible region of the electromagnetic spectrum. We will click on the buttons to review each of the electronic transitions individually.
All right, we're going to actually be calculating those electron transitions and the energies associated with those and the wavelengths. And that's really the value of this model, is that we can actually calculate the energies associated with these. So there's 2 terms that you should know. You should know the ground state is the lowest possible energy state for an atom. That is when the electron is closest to the nucleus. Okay, and that is the first energy level, right? So n equals 1. That is the first energy level. That's when the electron's closest to the nucleus. The highest energy state really an electron could be is gone. It could be completely removed. It can be an n equals infinity. Though typically we don't make then transitions, it really just depends on how much energy you have. When it's not in the ground state, that electron, then it's in the excited state. And again, the excited state is unstable, so it will return to the ground state. When it returns to the ground state, it releases energy in the form of light. Okay? We can calculate the change in energy needed to go from one state to another with this equation, where delta E is E of the final state minus E of the initial state. The final state is where the electron ends up. You can see that right here. The initial state is where the electron begins. Okay, in what energy level? It's the E, it's the N, right? So say it begins in N equals 1 and ends in N equals 2. A more useful form of that I will give you, okay, in just a minute. So, oops, sorry. If the change in energy is negative, then the atom's lost energy and is now in a more stable state because the electron moved closer to the nucleus. However, if it's positive, that means it absorbed and moved away from the nucleus. And again, as it moves, it releases energy. It releases energy in terms of photons of light. And usually each element is a particular color to our eye, but we can actually calculate and then observe the wavelengths with a prism if we look through a prism. So we've seen this equation before. However, we have seen this equation where we were solving for delta E. So if we know the change in energy associated with an electron moving, we can actually calculate the wavelength that's associated with that by using this equation, which was our change in energy equation that we already wrote down in our notes. So here's one sample problem, and this is not a very valuable sample problem, but we'll do it anyway just to get used to that first equation, which is another equation you should add to your list. It says calculate the energy corresponding to the n equals 3 electronic state in the Bohr atom. So to calculate the energy of one particular state of an electron, we use the equation E equals negative 2.178 times 10 to the negative 18th joules times z squared over n squared, okay? For hydrogen, Z is your atomic number that will always be 1. And we're calculating, sorry about that. So for hydrogen, the atomic number is already always 1, so Z will always be 1. 1 squared is 1. And we're going to, or we're in, n equals 3, the third energy level. So we have 1 squared over 3 squared. So we have negative 2.178 times 10 to the negative 18th times 1 over 9. And what we get is negative 2.42 times 10 to the negative 19th joules. Okay? So that is the amount of energy associated with the n equals 3 quantum number, or the n equals 3 energy level of an electron in hydrogen. That is completely unimportant. It tells us nothing. We cannot interpret anything from that. It tells us nothing. The value comes when you start calculating the change in energy as an electron moves from one energy level to the next. Like this next sample problem that you all have in your notes. Sample problem number 2. Calculate the energy change corresponding to the excitation of an electron from n equals 1 to n equals 3 electronic state in the hydrogen atom. So n equals 1 is our initial energy level. That's where we're starting. And we're ending at n equals 3. So our change in energy is equal to the final, the energy state of the final spot, our ending point, minus the energy state of our initial point. So we can calculate them separately and then subtract them, okay? So our energy of our final state equals negative 2.178 times 10 to the negative 18th, 1 squared over our final. We're ending at 3. That's what we just did, right? 3 squared. So our energy of our final state, if we calculate that, is equal to negative 2.42 times 10 to the negative 19th joules. We can then also calculate the energy of our initial state. I'm just going to put EI because I'm running, you know what, I'll do it down here. The energy of our initial state, which was n equals 1, right, is equal to negative 2.178 times 10 to the negative 18th times 1 over 1, which is equal to negative 2.178 times 10 to the negative 18th joules. And our change in energy is always our final minus our initial. The change in anything is always final minus initial. So we have negative 2.42 times 10 to the negative 18th. Excuse me, that's 19th. Minus 2.178 times 10 to the negative 18th. Two negatives equal a positive. So what you're really doing are negative 2.42 times 10 to the negative 19th plus 2.178 times 10 to the negative 18th, which turns out to be, if you add them together, 1.936 times 10 to the negative 18th joules. Since this is positive, energy is released. Energy is absorbed in this process. You're moving away from the nucleus, right? You're moving from n equals 1 out to n equals 3. So energy is absorbed, which is why really this is positive. So that all makes sense because we're moving away from the nucleus, okay? We will do sample problem number 3 in class tomorrow as a warm-up, but I do wanted to tell you there's a little bit of a shortcut for this. Instead of calculating them separately and then subtracting them, you can do this really in one step, where you just take negative 2.178 times 10 to the negative 18th joules is equal to 1 over n final squared minus 1 over n initial squared. And that makes your calculations a little bit simpler, okay? That's it for today's video. We'll do sample problem number 3 tomorrow, everybody. Have a great night. We'll see you. Bye-bye.